Welcome back to Arts Physics. In this video, we'll be going over what a force is, as well as all the kinds of forces that exist. Next video, we'll be going over Newton's laws, which directly tie into these. So stay tuned for that one. What is a force? A force is defined as a push or pull on an object resulting from its interaction with another object. So something important to remember is an object cannot exert self-force or a force on itself, which means an object can't exert a force on itself, right? Pretty simple. There has to be two objects that are coming into contact with each other. It doesn't need to be contact. It could also be non-contact, but it always needs to be between two objects, not one. One object won't work, okay? And this force is capable of changing an object's velocity, which is its speed and direction. The SI units of force are newtons, which are measured in base units as kilogram meter per second squared, which I'll give a more in-depth explanation for later on. But if you just look at F is equal to ma, if you're using SI units for mass, which is kgs, and SI units for acceleration, which is meter per second squared, then you're going to get kilogram times meter per second squared. Okay, that's why you always want to make sure that if you have a mass in grams, you want to turn it into kgs, because the force itself is kilogram meter per second squared. And a force is a vector, so it has both magnitude and direction. Okay, so a force has both a length or a value as well as a direction. So, like I said before, there's two families of forces: contact forces and non-contact or field forces. Contact forces are objects that are physically touching. Non-contact forces act at a distance. So normal force, I'll explain that in a bit, but just make sure that you note them down, right? That normal is a part of contact. You don't need to know what it means right now. I'll explain it in a second. Friction, tension, applied, and spring. They're all contact forces. Non-contact forces are gravity. So when you jump in the air, Earth isn't touching you, but it still does pull you down with the force, right? That's called gravity. Electromagnetic, which means that's how charges interact with each other. That's how electrons interact with protons, and vice versa. They don't contact each other. Magnetism isn't contacting each other, right? Magnets are placed a bit far from each other, but they still attract or repel, which is non-contact. So, these are the main courses we'll be going over, right? The gravity, electromagnetic, and strong and weak, which is in non-contact, but we don't need to look at strong and weak right now. We'll look at that a bit later. And that's not really the focus of this course. These are strong and weak nuclear forces. So first, let's go over normal force. Normal force is one of the newer forces that people learn because they're not exposed to it. What is a normal? It's what keeps you normal, is one way to think about it, okay? The perpendicular contact force a surface exerts on an object, always perpendicular to the surface, never along it. Which means that, for example, if you're standing on a ground, right? Gravity is pulling you down. Gravity. But what's holding you up, right? What's keeping you there without making you sink into the ground? That force is called normal force. It's the force that balances gravity's force and keeps you there. Okay, it acts perpendicular to a surface, which means it's always at right angle to the surface an object is on. So you see how this is perpendicular. And gravity is also gravity doesn't need to be at right angles. In this case it is, but normal always has to be at right angles. So if you had a ramp here, and if you had a block here, gravity would just pull straight down, okay? Gravity always just goes straight down. But normal would pull perpendicular to the block to keep the block, or perpendicular to the ramp that the block is on. So this is a ramp surface, and you can see the 90-degree angle here, right? Normal is always perpendicular to a surface. Usually it acts opposing gravity, but sometimes it doesn't need to oppose gravity. Like the ramp example we showed, it doesn't oppose all of gravity, which we'll look at later. And n is equal to mg. I'll go over that in a second, okay? That's not something you really need to worry about right now, but it is important. I'll go over it when I go over gravity as well. Okay. So let's look at gravitational force, or weight. Fg, or force due to gravity, is equal to m times g. M you can probably guess, right? That's the mass of the object. And g is the universal acceleration due to gravity, which is a new quantity, but it works out to be 9.81 meter per second squared, which is basically, if you jump up, what is your acceleration due to gravity? How fast are you going to be falling down? So that's velocity, but how fast are you going to be accelerating? This is relatively constant, right? No matter what place you jump off of, or no matter where you jump off of, you're going to still end up with the same acceleration of 9.81 meter per second squared. And you might see some textbooks rounded to be 10 or 9.8. And I mean, you can do that, but in general, it's 9.81. Okay, so in free fall, which means gravity is the only force acting on you. So this is also something you want to memorize, right? Free fall is gravity only force. So no other force is in free fall. That means gravity is the only force acting on it. And also, you can think of what objects are for free falls. Projectiles, right? Remember when I was going over projectile motion, I said projectiles are objects that are only acted on by the force of gravity. Well, we can see how that relates over here. So for example, if you had a mass of 5 kgs, then your force due to gravity would be 5 kgs times 9.81 meter per second squared, which is acceleration due to gravity, and you should get around 49 newtons. So I use 9.8 here, which gave me exactly 49, but if you use 9.81, you might get a slightly different answer. Now you can understand that if you're standing on a surface, right? If you're the stick man over here, you're standing on a surface, mg is still going to be pulling you down. It's not just that when you're in air, it pulls you down. Gravity is always pulling on you down. So what's going to push you up? That's going to be normal, right? And think about what needs to happen here. Should the normal force be greater than the gravity force, lesser than the gravity force, or equal to it? If it's lesser, that means gravity is going to end up pulling you down, right? Because gravity is greater. And then that doesn't make sense because you're not usually pulled down by ground. So then, what if normal force is greater? Then that means you'd be pushed up by the thing. So you wouldn't be able to stand on the ground. You'd be pushed up by the ground, which is also not the case, right? So normal force has to equal force of gravity, at least when you're on this, okay? So not always, it's not always, but at least when you're on a straight plane, your normal force has to equal your force of gravity to keep it balanced and to keep you walking. If your normal force is greater, you'd be floating. I mean, you'd not be floating, but you'd be pushed up by the ground. If your gravity was greater, you'd be sunken into the ground. So since force of gravity is just mg, normal force also. So this is most often, but not always. But in this case, normal force is mg. That's why over here I said normal is mg, because it has to counteract the gravity vector. Now let's go over friction, static and kinetic friction. So we're going to be using both of these pretty much equally often in this course, so you want to know both of them by heart. force static is equal to mu static times n, and force kinetic is equal to mu kinetic times n. So force static doesn't need to be equal to this, okay? It could be lesser. And we'll see what I mean by that. So there's two ways to write this. You can write this as force of friction, which is force of F, friction, or you could write it as Fs, so friction static. Either way, I mean, both of them make sense, so you could do that. I guess when you write FF, it's a bit confusing, right? Because you don't know whether this is static or kinetic friction. So you could just do Fk and Fs. So the difference between these two is, before that, let me explain what mu s and mu k are. These are just values, okay? These are just ratios based on how slippery the floor is, okay? On how slippery or gripping the force is, or how slippery or gripping the floor is, okay? It depends on the floor. So each floor will have a different constant for static or kinetic friction. And these are always going to be between 0 and 1. Okay, because they're just ratios. They're not really values by themselves. It's between 0 and 1. And what is this n here? That's not just newtons, right? What force was denoted by n? The normal force, exactly. So friction kinetic is mu k times the normal force. Friction static is mu s times the normal force. Okay. The normal force, as I told you, was the force that the ground pushes up on you to keep you from sinking in due to gravity. And sometimes this is equal to mg, but not always, right? And I'll show you why. If you assume that it's always equal to mg and you do mu s times mg, sometimes you can get it wrong. Now, what is the difference between static and kinetic friction? Kinetic friction is while you're moving, okay? So while you're running, for example, the ground has to be pushing you backward, right? Otherwise, you'd be slipping on the ground. And for example, if you're kicking, or not exactly kicking, for example, if you were throwing a ball, okay? If you threw a ball and the ball was rolling on the ground, if the ground exerts a force on this ball, okay? It exerts a force called Fk, or kinetic friction, which eventually slows the ball down to a stop, right? Which makes sense, because otherwise the ball would just keep on going forever. So there has to be some force that's acting on it, because you've noticed, right? Whenever you throw a ball, it tends to come to a stop because of force kinetic. Force kinetic is for kinetic friction, which means when the object is moving. Okay? So, later when I cover Newton's first law, you'll understand that objects in motion stay in motion unless they're acted on by an external force. This is the external force that's going to counteract this. And almost everything on Earth has friction. And it's going to counteract the direction of your force. So if the ball is coming this way, the friction is going to go opposite, okay? Friction is always opposite to motion. Kinetic friction is, not just kinetic friction. In general, friction is opposite to motion. Now we know that's kinetic friction, but what about static friction? So imagine you placed a book on a ramp. Okay, so let me draw a good book here. And you place this book on a ramp. The book is not going to immediately fall down if you lift the ramp up by a bit, right? It's going to stay for a while. So if you tilted something up, objects tend to stay in place for a bit and then they start to move. If you want to try it, then if you have a desk, try putting something on your desk and then tilting your desk to a bit of an angle. Not too much, just to a bit. You'll notice that the book doesn't move, right? Only when you tilt it higher, the book is going to move. Static friction is when the object is not moving. That's what static means, right? It's not changing, not moving. Kinetic means it's moving. So it makes sense that static friction is going to be not moving. So friction, kinetic, means when the object is moving, it's going against that. But friction static means before the object even moves, it's going to act to stop it from moving. Okay? The force of gravity, or something that whatever pulls this book downwards, has to be greater than friction static. That's when it's going to move. Okay? And also if you try pushing a really heavy thing, you notice how it doesn't move for a bit, right? That's because of friction static. It's pushing on it this way. You have to make it go the other way. Okay? And that has to be lesser than or equal to mu s times n. Which means friction static depends on a few things. First, it depends on mu s and n, like obviously, right? And then every object at a particular angle or just at rest is going to have a particular friction static, okay? And your force, so your friction static, assume you're pushing this way, your friction static, if it's greater than this force that you're using to push, you're always going to stay at that place. So Fs is mu s times n. And if you have a lower force, then it's not going to move, right? Because friction static is going to match your lower. So think about friction static as an enemy, okay? A very wise enemy who studied war and tactics and all that. And it knows how much force you're going to exert, okay? And it matches that force. But if you exert too much force, it's going to try matching it, but then it's not going to be able to, okay? There's a maximum value that this friction static can exert to keep it there. Once you push hard enough, the object is going to start moving. Okay? So always remember that. Friction static can change, okay? But the maximum value is going to be mu s times n. That's why it's lesser than or equal to mu s times n. If your force that you're using to push is greater than mu s times n, the object is going to move. Otherwise, it's going to stay in place. So yeah, friction static isn't defined, but the maximum value is, which is mu s times n. Otherwise, it doesn't expend its resources and it just pushes to keep it in place. Because if friction static was always at its maximum, then the object would be actually moving this way, right? It just counteracts your force, and then if you exert too much, the friction static maximum is overwhelmed and you're pushed. And you push the bots as well. And the maximum is given by this. That's why this is lesser than or equal to, because friction static could be lesser than this. Now, air resistance. So this isn't something we'll be going over too much in depth. I just wanted to show you though what variables affect air resistance. Because sometimes you might be asked, is an object with higher surface area or lower surface area more prone to air resistance? So this is called drag, okay, because it drags the ball upwards. Not a ball, but whatever is falling, mg is pulling it down. And since we don't have a normal force, because there's no surface here, there's going to be drag of air that pulls it upwards. So CD, so the formula for this is 1/2 CD, P times A times V squared. Shape, or drag coefficient. So CD is the shape of the object, okay? Or the drag coefficient of the air, because some air is a bit different, right? This P is air density. So it's not exactly P, it's a Greek letter, which I forgot, but you don't want to go around calling this P, okay? And then A is cross section. which means if you're falling, but you look like your rectangle is over here, right? Okay. Let's just say this is an iron block, okay? And it's falling, and its rectangle is over here. But the thing is, if you had a larger circular block with more cross-sectional area, which is just what is being affected, right? What is actually falling? Where's the air hitting at? That's going to be the cross-sectional area, or just the bottom of the block. The air is not going to touch the front of the block, just the bottom of the block, okay? So if your object has a greater cross-sectional density or cross-sectional area, then that means your air drag is going to be higher, which makes sense, right? If you throw a large cloth, it's going to take a larger time to land than a smaller cloth, because the air has more push up on, right? Because air is just particles. The more surface it has to push on, the more it's going to be able to push on. So higher surface area means higher drag. So this is a common misconception, right? If you drop a iron block, or if you drop a plastic, let's just say cloth, right? Not a plastic cloth, just regular cloth with large surface area or cross-sectional area, which one is going to have more force of drag? You might assume it's the block, right? Because the block is going faster, but it's actually this thing. Unless you start with the velocity initial. So it also matters times the v squared, okay, what the velocity is. Because if you're falling faster, your drag is going to affect you larger. Now let's go over applied force and tension. So tension is a force in a string. Okay? So basically, if you have a rope which is attached to an object and you're pulling using your hand, right? Tension is what is going to keep the rope intact without the rope breaking apart. Okay? Tension is the force of elasticity. It's any push or pull exerted directly by a person or object, but matched by a rope or a string or a cable, okay? It's the pulling force transmitted through these objects. Always pulling and never pushing. Because that's what you use, right? You use it in pulleys. Tension force you use to pull the rope and the water comes up. There's a lot of stuff tension is used for, okay? And it doesn't have a general formula because it usually matches the thing pulling it. So it doesn't have a general formula by itself, but springs do, but tension in general doesn't, okay? It just, you see how these are pointing to each other? That's the tension of the rope. So if the rope is being very tense, that means it has a lot of force on it, right? That's why we say tense ropes, or imagine a very strained rope that's almost about to break. That rope is going to have a lot of tension. That's why tension in general is just like how intense something is, right? And also, not just that, but there's also another force. So you might be like, okay, well, what if I just push on an object? What force is that? That's just called applied force, the force you apply, okay? It doesn't have a calculated value per se, just how much force you exert. So it's just called applied force. How much do you apply, right? You could apply a large amount or a small amount. Just something you need to know. Force applied. It's also written like FA, force applied, right? And also, there's another force called spring force, or the force in springs. Doesn't need to be per se springs, just objects that pull stuff back to the original position. So if a branch was pulled, but it's also pulling the monkey that's holding it back to the original position, then it's a spring. springs are just objects that pull or extend, that can extend, but can also pull back or push back to the original position, right? Because they can extend and they can compress. So that's what a spring is. And the force of a spring, because sometimes, you know how when you push on a spring really hard with an object, then that means when you release it, the spring goes bam, and the object keeps going very fast, right? That means the spring must have a force, right, to push on the object like that. So that's why springs are compact and extensive materials. And the more you pull on a string as well, the more force it's going to have. The more you stretch it out, the more it's going to want to come back to its original position, right? So the more intense you do something to a spring, the more force you get. And how is this represented in an equation? It's represented in Fs, or force spring, but you can just write Fs is equal to negative K adds. K is just a constant that differs from springs, right? Some springs might be more compact, some might be more stretchable, just a constant. And x is the distance from equilibrium. So when you buy a spring, it's going to be at its natural length, okay? It's just going to stay there. But if you pull it a distance x, then it's going to have a force proportional to that, which makes sense, right? If you pull a spring larger and your x becomes larger from your natural position, then you see how your force increases proportionally, because these are directly related. And then if you also compress something, so if you go like that, that's also x, right? Because it's at an x distance from its natural position. So the more you push it, the more closer it becomes to itself and away from its natural position. So x goes from both ways. There's no negative or positive x. Just what is the magnitude of the distance from the natural point of the spring to where you compressed it? How much did it extend or how much did it compress? So for example, if you had, and you understand why K would be in units of newtons per meter, right? Because if force of spring is in newtons, and if x is in meters, then what is going to multiply here to give you just newtons? Newtons per meters, right? Whoops. Yeah. Okay. So if you want an example, look at this one. K is equal to 200 newton per meter, and S is equal to 0.05 meters. What is energy in the spring? Or what is, not energy, sorry, that's completely different quantity. What is the force in the spring? Force of spring is equal to K, 200 newton per meter, times 0.005. So just 0.05 actually meters. Multiply these two, and you're going to get newtons, 10 newtons. And what is this negative here? Okay, that's a bit, doesn't mean the force itself is negative. It means it's in the opposite direction of the distance it was extended, okay? So if you count this, if you use a force applied to pull this string, negative means it's going to be in the opposite direction, the force of spring. Okay? Which makes sense, right? When you pull it in the rightward direction, it snaps leftward. When you compress it in the leftward direction, it snaps rightward. So that's what the negative here means. It doesn't mean the force itself is negative, just in the opposite direction, because force is a vector quantity, right? That's all it means. So I wouldn't advise putting this negative here in front of the sign, but you could if it helps you. But sometimes it's just how much force, or the magnitude of the force, okay? The negative just means it's going in the opposite direction of your pull. It's always going to seek equilibrium, okay? So it's if it's extended from equilibrium, then it's going to go back towards equilibrium. If it's extended, in the opposite direction, then it's going to want to go to equilibrium. So equilibrium is its natural length. Where does it stay naturally? What's its natural? Yeah, what's its natural length? And if you extend that, then that's your x. How much do you extend it? Okay. So as always, try and solve some of these problems. I'll go over more comprehensive problems as well, but keep in mind, this is just an introduction, right? This isn't as complex as you would expect. So just try it out. Which one is contact or non-contact? So I'm just going to write a C or NC for all of them. Tension, the forces need to contact with each other, right? Because you need to pull on a rope, or the rope needs to pull on something else. So this is going to be contact. Gravity is non-contact because I can jump in the air, but Earth will still find a way to push me down. Or, pull me down, right? Friction is contact because you need to be on a surface. You need to be moving or static on a surface for friction to occur. And normal force, same thing, contact, it's on the floor, right? It keeps you up on the floor. Electromagnetic, that's between charges, so that's non-contact. A 7 kg block rests on a table with extra 15 newtons pushed straight down on top. Find N, which is the normal force. So let's draw a free body diagram, which I'll go over more in my other videos, but let's just draw a simple one for now. 15 newtons is pushing down, right? And then we also have the force of gravity here, which is going to be 7 times 9.81 because the mass is 7. So 7 times 9.81 newtons here. And then that's going to give you, so you could round to 10, right? So a lot of times 9.81 is rounded to 10 meter per second squared. So then this becomes 7 times 10, 70 newtons, and then 15 newtons downwards. So 85 newtons is being pushed in this block downward. What's keeping the block upward? Normal force, right? And if the block is not smashing in through the table, that means normal force has to match this force. So it's going to be 85 newtons to match it, right? But it's going to be in this direction, while 85 newtons for pushing and gravity is going to be in this direction. All right, so now let's go on to the other two. Static versus kinetic. A 4 kg block has mu s is equal to 0.5 and mu k is equal to 0.3. By the way, it's pronounced mu, so MEW. Find mat static friction and kinetic friction force. Okay, so mat static, F mats S is always equal to the block. So first mu s 0.5 times 4 kgs, right? Or 4 kgs times what? Think about it. It's 0.5 times the normal force. If the block is just on a plane surface, which is what you should assume here, then if mg is the force pulling it down, normal is going to be the force matching that force. So normal is just going to be mg, right? Which is just 4 times 10, which is approximately 9.81. 0.5 times 4 times 10, that's 2 times 10, which is just 20 newtons. Okay, that's the F mats static. And then let's find kinetic friction force. F kinetic friction is going to be equal to mu kinetic, which is 0.3, times, same thing, right? 4 times the force of gravity, because the block is over here. So the normal force is just going to match the force of gravity, which is mg. So 4 times 10, or 40 times 0.3, 40 times 3 over 10, right? So this should just give you 12 newtons. Pretty straightforward, right? So a spring with the K constant, or a spring constant of 150 Newton per meter is compressed to 0.08 meters. Find the spring force and its direction. Okay, so assume a spring, natural length here, and then it's compressed like this. The distance is compressed is 0.08 meters. So what is the spring force going to be? Force spring is K, which is, let me get that back, 150 Newton per meter times distance, right, which is 0.08 meter. And I'm assuming you have your calculator with you, right? Because a lot of force calculations require a calculator. So let me boot that up and get back to you. Right, so that's gonna, the meters are gonna cancel out here. 150 times 0.08 is 12 newtons. Remember how F is equal to negative Ks, right? So this is negative 12 newtons, or you can just write 12 newtons. And the direction is going to be, since it's compressed to the left, it's going to be to the right, because it always want to go back to natural length, right? If it's left away from the natural length, it's going to go to the natural length in the right direction. So that's it for today's video on forces and all the types of forces. Next video we'll go over Newton's first and second laws, and later the third law as well. And if you're feeling like these problems are too simple, I understand that there's more complex problems, and we'll be going over those as well. This was just an introduction, okay? So all the more complex and all the more tricky problems, which is my goal to prepare you guys for, we'll go over later.